Hi, this is Gamma Di Gamma. Welcome back to my YouTube channel. So, in this video, I'm going to actually continue this trend of proving theorems from geometry. And the method that we are using is usually taking vectors in R2, or since the last video, I've been using complex numbers. Now, there were some questions about the uh, equivalence of the two methods. Now, I want to tell you that R2 is isomorphic to C. The two-dimensional, the Cartesian product of R with itself, which is R2, which gives a tuple of real numbers x comma y, is isomorphic to a complex number z given by x plus iy. And that's why these two methods are equivalent. So when I say z minus y, where z and y are both complex numbers, I actually mean, sort of the difference of both of these vectors, where these are vectors of R2. So, Z and Y would have A, B, or in CD, where A, B, or CD are basically the components, X and Y components. Okay, so let's get started with this video. Okay, so let me start with the construction first, because this is a theorem in geometry, so we need to really know what geometric shape or line segments or loci we're actually considering. And the construction is kind of simple. So we actually construct an arbitrary triangle ABC, which is here, and we form equilateral triangles from all the sides of the triangle. So equilateral triangles from side BC is going to be BDC, and similarly we have triangle AEC, equilateral triangle AEC from side AC, equilateral triangle AFB from side AB. Okay, next we connect the centroids of each triangles, or each of the equilateral triangles, to form this triangle GHI, this red triangle here. And now Napoleon's theorem claims that GHI is an equilateral triangle. Okay, it's a little more involved, I would say, than the previous two videos that I have on my channel. But nevertheless, the method will remain the same as the last video, which was Botema's theorem. So let's get started actually. Well, we will start by actually labeling each of the vertices of triangle ABC with some complex number, which denotes the coordinates of that point. So let's say this is 2z. Now I will be adding a factor of 2 everywhere for all of these, just because of computational reasons. There's nothing else to it really, because I don't want to deal with fractions of where the denominator is 2. Okay, moving on. So this is 2z, that's 2x and 2y. Fair enough. Now we need to actually find the coordinates of this centroid I, coordinates of centroid G, and coordinates of centroid H, then get the vector here, and then basically show that this vector has the same magnitude as this vector, has the same magnitude as this vector, because it's supposed to form an equilateral triangle, and therefore the sides must be all equal to each other. So we start by actually finding the midpoint of side AB here, and I'm calling that f prime. So f prime actually is going to be just the midpoint theorem. So 2x plus 2z, 2x plus 2z divided by 2. And now you see why I have the 2 in the first place, so that I don't deal with the fractions and I just get x plus z. That is actually the coordinates of point f prime. We can find the vector bf prime. which let me just sort of draw roughly. It's going to be this vector bf prime. We basically do the head minus tail gimmick to give us z minus x. I'm kind of skipping steps because I'm assuming you sort of saw the last few videos. It's really the same procedure. Now the main thing is to find the vector f prime I, which is basically this vector here. Because once we have that, we can just add the coordinates of f prime and then just get the coordinates of I. Because if vector is the head minus tail. So that's it. That's essentially the main formula that we're actually going to use. There's nothing else that we're doing here. So for that, I just want you to notice that since I is the centroid by construction, and it's this triangle FBA is actually an equilateral triangle. So if we sort of subtend a line from B to I, again, it's not the straightest of lines. This angle here is going to be 30 degrees because since this is an equilateral triangle, it's not true for any generic triangle. Such a line going from the vertex to the centroid is not always the angle bisector, because the total angle here is 60, right? Each angle is 60, being an equilateral. This line joining the vertex to the centroid may not always be an angle bisector. So then this angle is not guaranteed to be 30 for an arbitrary triangle, only because it is an equilateral triangle that we're guaranteed this angle to be 30. And we will take complete advantage of that, because now we can do trigonometry on this small triangle BF prime I. So if we do trigonometry on triangle BF prime I, we will see that we actually have tan 30. If we look at that tan of that 30 degree angle, F prime I over BF prime. Now we know what the magnitude of BF prime is. It's basically the magnitude of z minus x, because the magnitude of the vector BF prime is going to be BF prime, the length here. So it's just going to be magnitude of this guy. So that gives us that the magnitude of f prime I is actually tan 30, which is 1 over root 3 times the magnitude of BF prime. But that's just the magnitude. What about the direction? Well, if you look at this vector BF prime here, the vector we want to find is f prime I, and you notice by construction it is actually perpendicular. Now again, this line from f prime to I is only perpendicular because it's an equilateral triangle. There's some special properties with the centroid. The centroid is also the median of the triangle, and a bunch of other things are true. That's why we have these nice properties. Without any of these, we would not have such results and such assumptions going on. So we know that it's a 90 degree angle here. So all we have to do is just multiply BF by the factor of I and scale it by this root 3, because we know that the magnitude of fi prime is 1 over root 3 magnitude of BF prime. So what I mean is, so vector f prime I is going to be, first of all, it is going to be, we use the tan 30, right, because of this magnitude calculation here of BF prime. Now BF prime is z minus x, so that will give us the magnitude, but that won't really give us the direction. The direction, as I said, is subtends an angle of 90 degrees. So it's sort of rotating this vector BF prime by 90 degrees counterclockwise to get vector f prime I. So we're going to have a factor of I come in here because they're all complex numbers, and that's exactly what we did in the last video. So this is going to be I over root 3 times z minus x. Now I'm going to use this procedure for all the other sides, because that's all we need. But before we proceed to the other sides, let's just complete the calculation and find I. I is just vector f prime I, and then add the coordinates of I, of f prime, sorry, back to it. So we get x plus z plus I over root 3 times z minus x, and that's it. That's where we're done for this side. We're done for the first side. Now we repeat this entire calculation. Now the thing is, we don't need to repeat this trigonometry. We'll just remember that this factor of 1 over root 3 and this factor of I will sort of remain there, because this is true for even this side, even this small triangle that we will construct by joining C to G, for example, and similarly by joining A to H, for example. This entire geometry will be true for each of these equilateral triangles corresponding to each side. So I will just sort of try to do that as fast as I can. I don't want to spend too much time and therefore elongate the video. So D prime, the coordinates of that are going to be the midpoint of BC. So that's going to be x plus y, and then we have vector CD prime is going to be x minus y. We have D prime G, similar to the entire geometry, the entire discussion before, is just going to be I times root 3, I over root 3, sorry, times vector CD prime. So we're basically going to have I over root 3 times that x minus y, because of again the same discussion as like the geometry, that we have a 30-degree angle there, and then we can find the magnitude, and once we have the magnitude, we can also account for the direction, because we know it's like perpendicular. D prime G is perpendicular to CD prime, and therefore you get the factor of I coming out of it. Anyways, so then in the end, after all of this, we know what the coordinates of point G are. They're just x plus y. Just add d prime to vector dg. So I over root 3 and x minus y, like that. Okay, perfect. We will move on to the next side. I'm not gonna spend too much time. This side now. So let's find the midpoint of AC, which is E prime. And trust me, the biggest concern I have is keep to sort of ensure I keep changing the color. Okay, so E prime is y plus z. AE prime vector is y minus z, and E prime H vector, using the entire geometry discussion, is I over root 3 times y minus z. Perfect. H is actually going to be just add E prime back to it, so y plus z plus I over root 3 times y minus z. Perfect, wonderful. Now all that's left to do is find each of those side vectors for that the red centroid triangle. So this is the red centroid triangle, which we have to show is equilateral. So for that, we can just consider the side vectors. So by side vectors, I mean vector GI, vector HG, and vector IH. So I will just write them down. So vector GI, again the head minus tail business, is just z minus y plus I over root 3 times z minus 2x plus y. This is just algebra. Vector hg is x minus z, it's I over root 3 times x minus 2y plus z. The next is vector ih. I'm maintaining some sort of cyclic order because that is important. You'll see why. Y minus z plus I over root 3 multiplied with y minus 2z plus x. Now, let's just consider the first one. Again, now, if you can show by brute force that the magnitudes of each of these guys are the same, then you're done basically. But the magnitude calculation is a little more tedious because these are complex numbers. They have a real part and imaginary part, and you have to club each of them together, take the, square each, add them up, and then take the square root because that's like the complex modulus. That is a little tedious. So what we're going to do is actually, I'm just going to rewrite this, and you'll see in a minute why I'm doing that. So I have x times, I'm going to group the x, y, and z terms separately. So x is minus 2y over root 3. This is just rewriting and grouping terms, folks. So do not be confused. Y times, let's see, minus 1 plus I over root 3 plus z times I 1 plus I over root 3. Okay, perfect. Now what I'm going to do is I'm just going to consider this separately. We can sort of separate this out from the rest. Is I'm going to actually multiply this this thing here, the vector gi, basically the terms of vector gi, with this e to the I 2 pi over 3, and you'll see why. This is a rotation by 60 degrees actually, because if we do that, let's see what's going to happen to the x first. So the x has an I here, right? The x has an I here, and this is so I is actually e to the I pi, and then if we multiply by this additional phase, we do the quick algebra, we get e to the I, taking a common denominator, 7 pi over 6, which is e to the I pi, and e to the I pi over 6, which is a 30-degree rotation and multiplication by an I. So what that does to this x is the factor on the x will actually become 1 plus I over root 3. I'm just doing the calculation quickly. Plus y times, now if I do this entire procedure on the y, it's going to be a little long, but it'll get 1/2 minus root 3 over 2i minus 1/2 minus I over 2 root 3 plus z times negative 1/2 plus root 3 by 2i negative 1/2 negative 1 over 2 root 3i. And when I simplify this, actually, I'm gonna end up with hg. So this is just gonna be hg, right? I mean, you can just simplify this a little more. Like the halves, like here, the halves cancel out. Here, the halves add to give a 1, and then you can confirm actually that this is actually hg, the second side vector. And then similarly, if I multiply by another factor of e to the I 2 pi over 3 to hg, then that will actually end up giving me ih. And that's why you see the cyclic order was important, because all we're doing, each side is actually just a rotation of the other side by an angle of 60 degrees. And since this factor of rotation has actually has magnitude 1 actually, because e to the I anything has magnitude 1, All these guys have magnitude 1, so we are not actually changing the size of any of these guys. Our vectors are actually just given by gi, they're actually generated by gi. We multiply this factor and we get the other side, and we multiply by the factor again, so that's multiplying by 4 pi over 3, and we get the third side. So that's the sides of the triangle, and we know it's equilateral because the magnitude of this guy is equal to the magnitude of this guy is equal to the magnitude of this guy, because the magnitude of e to the I phi, where phi is any phase or any angle, is 1, and this is the complex magnitude. So maybe 2 bars or 1 bar, it's up to you. And that is why, folks, it is an equilateral triangle. And again, it makes sense that each side is just rotated by 60 degrees, because the angles in an equilateral triangle are 60 degrees. So it's indeed, this vector getting rotated. Sorry, this vector, because we're talking about the red triangle, the red vector getting just rotated by 60 to fall onto this vector. This gets rotated, falls onto this vector. And that's why, this orientation, this cyclic orientation of the vectors was important, so that we sort of generate one from the other without sort of having to reverse the orientation of the rotation. Like we're going in either clockwise 2 pi over 3 rotation or anti-clockwise, but we're not sort of mixing them because we chose the vectors, we defined the vector. We could have chosen this as vector ig, we chose gi, and then therefore hg and ih to complete a cyclic orientation, and when we don't have to sort of change the kind of rotation that we're doing. So let me just say that this is cyclic, this is a cyclic rotation or cyclic choice of these vectors will sort of satisfy this tuple that we have here, this tuple. Now if we just take any of these points to sort of be unit, just the trivial vector, or just sort of ignore them out, we will notice that 1 e to the I 2 pi over 3, e to the I 4 pi over 4 form an equilateral triangle. And you might know this from complex analysis to be the cube roots of unity, right? And we know that the cube roots of unity form an equilateral triangle in the complex plane. These are the cube roots of unity. So you see how this one theorem actually connects many of these aspects from algebra, from geometry, from complex numbers, complex analysis. And that is why I really wanted to do this theorem, because it's connecting so many aspects of mathematics together. Now I will actually give you a small demonstration of this theorem in practice. I forgot to put the proof box. I'm going to give a small demonstration of this theorem in practice using our friend GeoGebra geometry. Okay, so here we have an arbitrary triangle ABC, and we're just going to move the points because we're free to move the points since it's an arbitrary triangle. And these green triangles are actually the equilateral triangles that are formed from each of the sides of ABC. So that those will remain fixed. So we see you can't really move this around because the only degrees of freedom are in ABC. And then GHI are the centroids, and the centroids will also sort of evolve according to how we change ABC, because they're the centroids of those green equilateral triangles, and therefore the triangle formed from those centroids, triangle GHI, will also be changing. So let's see, we're changing, but you see sort of like the distance between GH, HI and IG is the same. They're always equidistant from one another, no matter what I do to A. And let's play with B. Yes, see, nothing really is happening. They're all expanding and contracting by the same rates, which is quite fascinating. Now this theorem was named after Napoleon because they say he sort of discovered it along with Laplace. I'm not going to go into the history. People debate that, whether Napoleon actually did it or it's just some misnomer for the theorem. But anyways, this is a cool theorem. Napoleon's theorem has a mighty name and is quite an interesting theorem. So you see, this is fixed. Now there's one version where you don't take you take the equilateral triangles not outside the original triangle but inside, and then this theorem still holds. Again, the proof is should be similar. There's another sort of property, not theorem, I would say, that says the difference of the areas of these outer equilateral triangles minus the inner equilateral triangles is the total area of the original triangle. Now you can prove that if you want. I'm not going to do it, but this is again food for thought. And I think that's it for this video, guys. Thanks for watching. Please share this video with your friends if you enjoy it. Subscribe, like, share, and peace out. See you next time. Bye.